So I was delighted to be invited to talk at this HAXPES showcase. Ever since Wendy and Ben were fortunate enough to buy a HAXPES instrument, we've been working closely with them. And our role has really been helping to understand the data or get better use out of the data. And what my intention here was to talk about was to say, what might you use HAXPES for in a practical concept of a lab-based instrument? So I'm not going to really be talking about synchrotron-based HAXPES measurements. I'm not going to be talking about the really elegant studies that can be done on such instruments with angle resolved work and photoelectron diffraction, various things like that. But what would an average user want to get out of the instrument, and what could be done that can't be done by other techniques? Now, when I was preparing the talk, I talked to Ben, and Ben said, I don't know how many XPS users there are going to be in the audience. So if you have used XPS or know about XPS, can you put your hands up, please? Okay, so that's the majority. So a lot of this talk, you hopefully are already going to know, but it'll give you a nice warm feeling and get you into the flow for some of the talks that will be coming later. So my idea in this talk was to introduce some concepts in X-ray photoelectron spectroscopy, and then highlight some differences or similarities between XPS and HAXPES. But before I do that, I wanted to say a little bit about the National Physical Laboratory. So who and what are we? Many people may not, a lot of people don't seem to have heard of us, but we are the highest point of reference for most measurements that are made in the UK. So we are the National Metrology Institute. Okay, so we keep the UK's time. So we realise the second for the UK. We realise the kilogram. So the second is now can be measured so precisely that you can take an atomic clock invented at NPL, by the way. Put it on the ground floor here, put it on the floor above, another one on the floor above. And within a day, you can measure the time difference just from the difference in the gravitational field. That's how accurately you can measure the second. The kilogram is no longer a ball of metal held in a lab in Paris. It is realized through a balance that is basically a balance between the gravitational force and the electrical force. It's called the Kibble balance. That also was invented at NPL. So that is now the way that you realize these things. And the SI, which now underpins most global measurements, is defined in terms of physical constants. Apart from the mole, which is just a number. Well, don't tell anyone I said that. Okay, so we are owned by government as an arm's length body, and we're based in Teddington, but we also have operations in Strathclyde, Surrey, Cambridge, Huddersfield, Solihull, and also here in Manchester. We have a number of people who work here in Manchester, closely with either the Graphene Research Institutes, GEEK, and the Graphene Innovate. Doesn't have graphene. What's the other graphene? NGI. NGI, National Graphene Institute. Thank you. And with the Royce Institute. So we have a memorandum of understanding with the Royce, and in fact, part of that was the collaboration in HAXPES. That was one of the founding activities that occurred between NPL and the Royce Institute. So about 800 scientists at NPL. Not all of them do surface analysis. There's only a few of us. But we have a great breadth and depth of metrology, the measurement expertise in that space, and we collaborate widely with other national measurement institutes across the world, like NIST in the US, PTB in Germany, AIST in Japan, and CRIS in Korea. So The priorities of NPL are based around national challenges that the government sets for us. And there are a number of national challenges, some related to health and life sciences, some related to the environment, so measuring the greenhouse gas and the global temperature, that's important. One of those is prosperity, and I'll come on to that in a short while. But the point is that when we're addressing the national challenges, you need to have good measurement to make policy-based decisions and policy and regulation. So it's important for NPL to pay close attention to what the government is prioritising and make sure the measurement and infrastructure is in place. So one of our streams at the moment is digital assurance, and that's looking at things like artificial intelligence. How can we have trustworthy machine learning? If anybody is working in that area, wants to learn more about that, please talk to me. I'll put you in touch with the right people. So one of the government challenges is prosperity, and this is actually links very closely to what the previous talk. How do we underpin and support innovation in advanced manufacturing and advanced materials? And really, this is where the work we do in photoelectron spectroscopy sits. If you want to know more, please visit the website. Okay, so here's this is my slide to explain why industry is interested in interfaces. Now, if you go to any meeting which is dedicated to surface and interfaces, you'll find certain range of industries there, and they will range from the aerospace industry to manufacturers of hair lotions. So if you think about virtually anything you have, any technology on your body, on your person, that you drive around in, there are interfaces there, and those interfaces are critical to the function of those devices. So the joining of materials, so adhesion and bonding is critical. It's critically important that the interfaces are correct. Wettability and non-wettability, this is all determined by surface chemistry and topography. Things like organic LEDs in your phone, all of the interfaces there have to be engineered. The thicknesses of the materials have to be right. The concentration of the different components in each of the layers is also critical. And so all of these are measurements: the amount of material, the thickness of material, and so on. I've got another list here, and I know that we're going to have talks on semiconductors and batteries and fuel cells later on. But even things like hair gel, surface analysis for there. You don't get your hair sticking up like that without a bit of surface interaction. So the need for surface analysis is ubiquitous, and there are many methods by which you might measure surface chemistry and surface properties. Some years ago, this is actually quite an old diagram, we summarized most of the main lab-based techniques in this diagram here. And this is really about what kind of information is required when you're measuring an interface. There's three main questions. The first one is, what is at the interface? Is it the thing you expected it to be, or is it something you're not expecting to be there? And if there's something there, where is it? That could be either spatially located across the surface or in depth beneath the surface. And then the hardest question to answer is, how much is there? So I'm not going to go through all of these methods. I mean, what this plot does is try to answer on the y-axis the what is it, from a simple material contrast mechanism to full chemical structure analysis. And on the x-axis is the spatial resolution. That's the where is it question. I'm going to be talking mostly about XPS. So you see XPS, not great spatial resolution in general, at a micron if you push things. But it does give you quite a lot of information on the elemental composition, chemical states, and some sort of structural information. It also gives you some physical information as well if you interpret it in the right way. Underneath that was a yellow blob. That's secondary ion mass spectrometry. That's another very commonly used method. And that potentially can give you full structural analysis, but you have to interpret it in the right way. As you go down to smaller and smaller dimensions, you get less and less information. And that's just a physical restriction on the number of ions you can get out of the sun. So those are the two main industry methods for surface chemistry. There is another axis. You want to think about a z-axis. It's not on this diagram. And that is answering the how much is there question. And on that z-axis, the XPS, as you can see, is quite a way above the SIMS. It's much easier to get quantification from photoelectron spectroscopy than it is from secondary ion mass spectrometry. Two techniques actually pair together very well. I'm blathering about, I just realised that because I started a bit late, I'm going to speed up now. So what is photoelectron spectroscopy? As most of you in this room know, it was developed in Uppsala in Sweden by Kai Siegbarg, who got the Nobel Prize for physics in 1981. He started work on this in around 1953. And this, I was very lucky to go to Uppsala for a conference. And sitting outside the Siegbarg lecture theatre, the Angstrom Institute, there was the first XPS instrument. So I managed to get a photograph of that. I was very happy about that. I'm very proud of that photo. If you blow it up, you can even read all the text. So I called it XPS, but that wasn't what Kai Siegbarg called it. He called it electron spectroscopy for chemical analysis, or ESCA. And when I started out back in the late 1980s learning about XPS in Durham, we didn't call it XPS, we called it ESCA. Everybody called it ESCA. And then gradually over the years, shifted to XPS. And for those of you who are younger, you probably have only heard of ESCA in one context. And that is this film here, The Eagle, which was in 2011. And ESCA was a Briton from the tribe of Brigantes. The Brigantes actually were in this area. And he helps a Roman soldier travel north of the wall, Hadrian's Wall, isn't Game of Thrones, to recapture the eagle that was lost when the 9th Legion was wiped out in Hibernia. And I thought that was just a coincidence. But this is based on a book written by Rosemary Sutcliffe called The Eagle of the Ninth. And that was written in 1954. 1954, 1953. Conspiracy theories have been made of less. Okay, so why have I called this talk Practical HAXPES? And at MPL, there's a long history of improving the metrology of photoelectron spectroscopy, particularly XPS and other forms of electron spectroscopy, Auger electron spectroscopy. So we've been active in the area since the 1970s, and many of you will have heard of Martin Sear, who sadly passed away a couple of years ago. And this is my copy of what I think is one of the best textbooks you can get on XPS. It's got everything in it that you really need to know. And it's called Practical Surface Analysis. It's practical XPS. What you need to do, what you need to know if you're running and operating an instrument, you're providing data for other people, and you're doing this in a general analytical context. So I want to think that where we are now with XPS, in terms of standardization and reliability, reproducibility, is something we can get to much more quickly with HAXPES because we have all the experience with XPS. And the problems to solve are pretty much the same problems. So I'm going to go in the next part of the talk. What I'm going to do is I'm going to talk a little bit, talk about something about XPS, and I'm going to contrast that with HAXPES, what's different or what's not different. And we'll see how that works. So one thing I like this plot. It tells you that XPS is super useful. So at the turn of the century, there were just over 2,000 papers a year published on XPS, and you can check this out on Web of Science. Now we're heading towards 20,000 papers a year. That's a growth of tenfold. That's come, so that tells us what academia is doing, but I'm pretty sure this is also mimicking what's going on in industry. Industry is also using this because it's important for a lot of technologically important materials, such as battery materials and semiconductors. So XPS use is growing. There's a large number of users. That comes with some problems as people have to relearn some lessons that were learned many years ago. But the key point is it has to be useful or people wouldn't do it. I think that's a testament to people like Martin Sear, who spent a lot of time making sure that when you have an instrument, you can calibrate it and you can have some level of certainty in the outputs. Okay, so here's a similar graph for HAXPES. I want to thank David for putting this one, David Camp from MPL, for putting this one together. So this tracks publications and citations. And so it's increasing. It's not quite the exponential curve of XPS, but I think that's because supply is limited. So as far as I understand, synchrotron beamlines for HAXPES are overcapacity. They're completely used up, and there are not yet many places you can go to do lab-based HAXPES. So basically, as more instruments come in, I think that the demand should be growing and increasing. There's no reason that it shouldn't be. Okay, so as I said, a bit of XPS. This is an overview of XPS. If you've got a lab-based instrument, you've got several things usually. You've got an X-ray anode that produces X-rays of fixed energies. You usually have a monochromator, which rejects unwanted X-rays, so you get a much purer and cleaner light source. You have lenses that collect and retard emitted electrons and put them into the analyzer. The analyzers energy select electrons, and then you have a detector that's sensitive to a single electron impact. So I put all those together, and you have a functional XPS instrument. Now, most people want to get this value, EB, what I call EB, it's the binding energy of electrons. So I've written the equation in a slightly controversial format, and I'll come back to this later on. So what you're actually measuring is the kinetic energy of the electrons, which I call EK. And that's equal to the photon energy minus the binding energy of the electron in the atom, minus what's called the work function. That's an energy to get the electron out of the sample, and then minus the potential difference between the sample and the analyzer, or the analyzer earth. It turns out if you have a conductive sample in electrical contact with the analyzer earth, then that potential difference is known. That's simply the difference between the work function of the analyzer and the work function of the sample. You plug that into the equation, you end up with the bottom equation, which is the one that everyone should recognize, who does XPS. So from these three things, kinetic energy you've measured, photon energy you know, spectrometer work function you can measure. It's actually quite easy, there are ISO standards. So you know all of these, you can get the binding energy. But I want to just point out that only works if you have a conductive sample in contact, good electrical contact with the spectrometer earth. If not, you should maybe go back to this equation and think about it again. But the other thing I wanted to do, the other reason I wanted to put this in is because for chemical state analysis, at least a simple form of analysis, this is a good, taking notice of the local potential of the atom is actually a good way of thinking. So what about HAXPES? HAXPES, completely different? No, it's exactly the same. The same sort of instrumentation. The only difference is the energy of the X-ray source. And as a consequence, there's probably a difference in the analyzer, because you've got to get the analyzer to be able to measure high kinetic energy electrons. Now, very recently, ISO defined the term HAXPES as any XPS measurement that's over 2,140 dB. Why that? That's the only literature definition that exists. It's not a work by Wojcik. And it happens to be the lowest energy you can get to with a silicon 111 monochromate. So, magnesium K alpha XPS, aluminium K alpha XPS, silver L alpha HAXPES, all the way up to gallium K alpha HAXPES. So those are the main lab-based instrument sources that are currently in operation. The other thing, so one of the things that I wanted to also point out, I've talked about photoelectrons. There are other electrons that come out of the sample. And these are called Auger electrons. So when a photoelectron is knocked out of an atom, that leaves a core hole vacancy, which must be filled. It's a very highly excited state of the atom. An electron from a higher shell drops down to fill that, and some of the energy has to be carried away. It turns out that the main route, the main mechanism for carrying away that energy is for another electron to take it away, particularly at the energies we're talking. So these electrons are called Auger electrons, and they appear in spectra. They can provide useful information, because they provide slightly different information to the photoelectron peak. And if you've done XPS, you know that the Auger parameter can much more closely define the chemical state of the element than either one of the peaks alone. However, they can also be a problem. I tried to illustrate this with photocopies from the handbook of XPS by Phi, where I've gone from chromium to nickel in the 3D series. And if you notice with chromium, on this scale, for those of you who are not familiar with XPS, this is a wide scan spectrum. This is basically all the electrons coming off and what the intensity is at each of the energies. Kinetic energy increases from left to right. So from the equations I've given you before, the binding energy increases from right to left. But you always plot it with increasing kinetic energy. That's the rule. So the photoelectron peaks have high kinetic energy, and the Auger electrons have low kinetic energy. When you get to nickel, the photoelectrons have lower kinetic energy, and the Auger electrons have higher kinetic energy. As you go through that series, an increasing atomic number, the sets of lines cross until you reach a bit of a conundrum at cobalt, where they're completely overlapping. And that really causes some problems for interpretation. And if you're looking at battery materials, you're looking at a combination of all these elements together. So all of these things are overlapping one with another. So HAXPES, or at least having an alternative X-ray source with a different energy, can really help that. Here's another problem child for XPS, gallium nitride. So we know there's nitrogen there, but if you look at the yellow XPS spectra, it's pretty hard to spot because there's a load of gallium LMM, or gallium Auger peaks sitting right over where the nitrogen minus is. So the only way around that is to shift the photoelectron peaks to higher kinetic energy, so that you don't get that overlap. Then you can see the nitrogen 1s clearly. Now you can do a quantification and understand something about that material. How long have I got now?
Something like
10 minutes.
10 minutes.
All right. So I'm going to go fast. So here's basic interpretation of XPS. I'm not going to go through this very. So this is from Steve Barnes' Nobel Prize lecture. This is the first thing I saw when I did my PhD. It was amazing to me. So it's such a beautiful molecule, and you can line it up with the peaks in the spectra. There's key takeaway messages that you have the same atom in different chemical environments. You have different binding energies. And those binding energies, in the case of carbon, are really easy to interpret because they relate to the amount of positive charge on the carbon atom. If you have a lot of fluorine atoms, that's very electronegative, bonds to the carbon, pulls away electron density, and therefore increases the binding energy of the carbon. When you get to the other end of the molecule, you've got a hydrocarbon, which is kind of your reference voltage here. And because this is gas phase, that's 291.2 eV, not 285 eV, which is what you might expect for a solid state. So, binding energy changes with chemistry. But the other thing that's really nice about this, all these peaks have the same intensity because there are equal number of atoms in each of those environments. So that's a fantastic groundwork for quantitative analysis. And if you've ever done SIM, secondary ion mass spectrometry, you'd be amazed by this if you actually got something that you could directly understand without reference materials and a great deal of work. So, if you're doing compositional analysis, what you need to do is understand how different atoms respond to X-rays. So that's understanding the photoionization cross sections. Then you need to know where those electrons are going in space. So you have to understand the angular emission characteristics. In a solid, you've got to understand how the electrons get transported through the solid. And then at the end of all of that, you've got to understand that your analyzer may not be efficient, may not be identically efficient to all electrons at different kinetic energies. So you have to understand the analyzer efficiency. And this is just a comparison of HAXPES and XPS measurements of this ionic liquid. And we chose this ionic liquid, or chose an ionic liquid because it happens to be, you can make that and it's homogeneous in nature. And what you do generally when you're reporting XPS is report the equivalent homogeneous composition. So we can test from stoichiometry whether we're getting the right numbers. And they're pretty close, within one atomic percent or so. That's better than you might expect if you're doing things carefully and well. So what you need for quantitation is two things really. One is the calibration of the energy scale, of the intensity scale. For that, you need reference spectra. And so far as I know, although we have reference spectra for XPS, that have been around for a long while, we only have reference spectra so far for the silver L source. And we need them for the chromium K alpha and gallium K alpha source, commonly in use. The other thing you need is sensitivity factors. Now, if your calibration is accurate, calibration of the intensity scale is accurate, you can calculate the sensitivity factors from theory. And David Camp from MPL, who's sitting there and will be in the panel later on, has tabulated several of those with interpolation, so you can put any photon energy in and get the cross sections and the angular emission characteristics out. So that's available at the MPL website. The other thing you need to know is instrument geometry. I'm not going to dwell on this because if I try and explain this diagram, it'll take a little bit too long. But the key thing to note is there is a difference between XPS and HAXPES. Now, in XPS, you can generally assume that when electrons are emitted, they go out in a p orbital shape, or close to a mix between an s and a p orbital shape. So like a figure of 8 shape. So the photon comes in, and the electrons are ejected mainly along the electric vector of the the incoming X-ray. However, for higher energy photons, there's a bit of a forward or backward asymmetry to that, and that increases usually with the increasing energy. There are certain points, certain geometries where you can eliminate or very closely reduce those effects to being close to zero, so that there's no need to consider angular emission. And it actually turns out that the good geometry, which we call a magic angle, it's not really the magic angle. The magic angle is 54.74. But for HAXPES instruments, if you have this geometry, so if the X-ray is going to the monochromator and coming out at 45 degrees, that gives you a 2-to-1 polarization. And then you're at 90 degrees between the incoming X-rays and the outgoing electrons. That geometry is very close to a magic angle geometry for a lab-based instrument. For a synchrotron with plane polarized light, it's different. That happens to be pretty close to the geometry of the Scienta Omicron instrument. And that means it's been very straightforward to do quantification on that instrument. We don't have to take account of these angular emission. Okay, I'm now about to run out of time. I'm going to just tell you this simple picture that I gave you before, pretty good for carbon, not good for other elements. And this is just an example of cerium oxide. You don't get one peak, you get 6. Now, there's 2 pairs of 3 really. And this is due to shake-ups. You also have multiplet splitting, which this nickel oxide peak, green spectrum here at the bottom is showing. I think there might be 3 chemical states. No, there's only 1. You have to understand, if you're going to interpret the data properly, you have to have a level of expertise and read the literature. Can't just throw some peaks in and make it up. Key thing about XPS is the information depth, and this, in the last 5 minutes, was my main point. Should I get a little bit more time? That's very kind of you. So, the reason XPS is surface sensitive is that electrons don't travel very far through materials without losing energy. And this diagram shows you how many nanometers. So where the signal comes from gold is with magnesium cleaved alpha radiation as a function of depth. And you can see the logarithmic scale on the y-axis, linear scale on the depth axis, very close to an exponential attenuation. And you can basically use the Beer-Lambert law to understand the depth of signal in XPS. Some of these curves that you can see, particularly at the very high emission angles, that's because there's other types of scattering. It's not just the loss of energy. Electrons, if they scatter off atoms, they change direction. When they're losing energy, they're scattering off other electrons. But that exponential decay is the basis of most sorts of analyses where you're trying to get depth information from XPS. And what I wanted to point out is that contamination is a problem in XPS, and it may not be an obvious problem. This is clean gold and contaminated gold. When you subtract one spectrum from the other, they're taken under exactly the same conditions. You can see you've lost 25% intensity in the gold peaks, and that's only with 1 nanometer part of parts sitting on the surface. So although they look similar, they're going to give you very different results. And that's energy dependent because at higher kinetic energy, you have a greater attenuation length than you do at lower. The HAXPES is less affected by this. A bit of contamination in an XPS gives you a strong issue with quantification because it differentially attenuates signals from different kinetic energies. And it also if there's carbon in the sample, it can cause real problems. But if you have a HAXPES source, you're looking much more in the bulk, and the contribution of the contamination is much less. I'm going to skip that slide. Skip that slide. I just want to point out that, and this may be a surprise to some people, if you are measuring very thin film thicknesses, such as silicon oxide on silicon, the most accurate method for doing that is not TEM and cross-section, it's XPS. And this is the result of an interlaboratory study led by NPL and carried out at the highest metrological levels. All these other techniques, ellipsometry, TEM, Rutherford backscattering, so on and so on, they can't measure the thicknesses accurately by quite some way, up to a nanometer off. We recently rerun this study, but with hafnium oxide, and once again, TEM was the worst thing to use. I've already said that the attenuation length is closely related to the kinetic energy. So HAXPES gets you through thicker films, and these are just some examples of this 25 nanometer silicon oxide. You can't see through it with normal XPS, but you can with chromium K alpha radiation. And this is a comparison on zirconium oxide with the gallium K alpha source and normal XPS. This is from Scienta just here, just that. So this allows us to see buried interfaces. I'm going to go really quickly now. I'm not going to talk about band bending. I think the next speaker is going to say much more about that than I will. But if you want to go even deeper than this, you normally do depth profiling. Depth profiling with ion beams is a bit of a problem because you can change the stoichiometry, chemistry of the sample. You'll get roughening effects and all sorts of things. So this is not an ideal way of probing deeply buried interfaces or getting layer structures. But there is something that you can do, and that's ignore the peaks and look at the XPS background. Now, Sven Tugard's got a large number of papers on how the background shape in XPS changes with the depth distribution of material. So here we go from these all have the same peak intensity for copper. A, all the copper's at the surface. D, all the copper is underneath the surface. And here you're seeing electrons that have traveled through material and lost energy on the way out. Okay. It's quite complicated to apply that analysis to most materials because all the peaks are overlapping, the backgrounds are overlapping, and you need to have quite a thorough analysis. But I just wanted to say that HAXPES has a lot of advantages in this regard because the peak energies are higher, they're more widely separated, there's more energy to lose, so you can see very deeply indeed if you look at background shapes. And this is an example that I really like because I was involved in the work. At the bottom, the screen, this is an iridium compound buried under organic. This is used in organic LED displays, this compound. And you can see it and even measure the amount of material, the depth of the material, up to 200 nanometers. You can't see the inelastic, can't see the peaks, but you can see the background, and you can analyze that background. Okay. I'm not going to talk about charge referencing. I just say
we'll come back to that.
Carbon 1s, definitely not good for HAXPES because the peaks move around because of the recoil effect. And the cross sections are really small. So in terms of standardization, we've got a way to go. I just wanted to point out this has just been published from Remy Latoury's group in Paris. So he's run an interlaboratory study. I said French, but actually there's Belgian laboratories involved here as well. So forgive me, anyone from Belgium. This is the sort of work we need to do to make sure things are terrible. He's also developed a way of getting an approximate intensity calibration, which I think is certainly worth looking into. And so we need standards. So there's a new activity in ISO TC201, which is surface chemical analysis. There's a study group on standards for HAXPES. If you're interested in being involved in that, please contact David Kemp from NPL. These are the top priority items so far: sensitivity factors, transmission functions, energy scale calibration, and reference spectra. And we're addressing all of these. And finally, I want to thank everybody who contributed to the talk, and you for your patience and time bearing with me as I sped up, probably incomprehensibly, towards the end. And all of these people who contributed to the activity and some of the data that I've shown.